We are talking about the fundamental principle of counting, and we've kind of touched upon that in previous videos, but we're going to do this more formally. And that's basically this tree diagram. If one event can occur in m ways, and a second event can occur in n ways, then together they can occur in m times n ways. And remember when we did this, we have an event, and let's just say it can occur in m ways, and then a second event can occur in n ways. Then the total ways, because each of these, there's m of these, and they all have basically n branches, so there's m times n waves. And that's basically the theory. So we have an example. At a Baskin-Robbins, customers have a choice between plain cone and a sugar cone. There are 6 ice cream flavors: vanilla, chocolate, strawberry, butterscotch, lemon, and raspberry. How many different single scoop ice cream cones can be made? So there's 6 flavors. So that's 6 ways multiplied by 2 ways. Whoops. That's equal to 12 ways. And basically there's 6 times 2 different ways to order ice cream at Baskin-Robbins. Example 2. When buying a new shirt, Horokosaki, points if you know who that is, has the following options: striped, spotted, and plain. So 3 choices. And dress shirt, golf shirt, and t-shirt, another 3 choices, and of those, 10 different colors. So how many configurations? Well, you just do 3 times 10 is equal to 90. 90 different configurations. And you could see how a tree diagram would start to get really messy when we have 3, and then 2, 3, 4, 5, 6, 7, 8, 9, 10 times, there's 90 different outcomes at the end. So the fundamental counting principle comes in handy. Okay, so now we talk about a technique we can use. How many outcomes are possible when rolling a standard die? And I like to draw for each outcome or trial, I like to draw a square. And for 2 rolls, I draw 2 squares for 2 trials. And there's 6 possibilities for the first and 6 possibilities for the second. Therefore, a total of 36 possible outcomes. For 3 rolls, I just draw, now we're doing 3 rolls. I just draw a extra box for the trial, and and there's 6 possible outcomes again. So there's 6 times 6 times 6 ways, which is 216 ways. Now let's look at example 4, repeated independent trials. Okay, so a password consists of 6 letters of the alphabet. So 6 letters with repetition permitted. So I can repeat those letters. So I have 6 possible scenarios and 26 for each of them. So it's 26 to the power of 6. 26 times 26 times 26 for each trial, which is about 308 million. Okay. How many possible passwords are possible if capitals and lowercase is permitted? Now, you might be thinking, just multiply this by 2. But that would be incorrect, because I have 6 trials, and how many possibilities are there? Well, 52 for each. So it's actually 52 to the power of 6. So, that's not just double this. That's a lot more than that. It's 19 billion. So we went from 308 to 19 billion. Counting without replacement. So before, remember when we were doing our tree diagrams, if we had 3 choices and another 3 choices.
Miss Masterton and Miss Kadir, please go to room 218 for the science meeting for MYP. Thank you.
And then another 3 choices, it would be 3 times 3 times 3. But if there's no replacement, then this last one came out, and there's 2, and then there's 1 left. Anyway, we'll see this in play with this example. So we have a deck of 52 cards. If you draw 2 cards, one after the other, how many possible outcomes are there? And we don't replace it. So the first scenario, that's the first scenario, we have 52 choices. But in the second scenario, we only have 51 choices. So using the fundamental counting principle, we multiply 52 by 51 to get 2,652. So there are 2,652 possible outcomes when choosing 2 cards without replacement. Next example. From a class of 26 students, how many ways can you form a 3-person committee with 1 chair, 1 note taker, and 1 treasurer? So we have 3 positions, and 1 is a chair, 1 is a note taker, and 1 is a treasurer. So essentially, you have 26 choices for the chair, and then you have 25 choices. You have 25 remaining because you can't hold 2 positions. And then 24 are left for the last one. So the fundamental counting principle states that we multiply all the possible outcomes to get 15,600. Now you're saying, well, what if we did the note first and the treasurer first? Well, it doesn't matter what goes first. It's how many ways can you form a 3-person committee, not orders of how you form them. Okay? And that's it. Do the rest for homework. This is page 73 in the text, all of these questions.